take a look at some Ztransform properties. These are in section 5.2 of their text. First property that we'll take a look at, probably one of the most important properties, is the delay property. So here, the notation we're using, the Z-transform of the causal sequence x of n, u of n is equal to x of z. So this is the notation that we're using. Again, x of n here may be infinite in duration, but we're only dealing with causal sequences, so we can multiply that by u of n to apply our Z-transform. And we're interested in then finding the Z-transform of a delayed version of this sequence, and you can work through the definition of the Z-transform, the summation definition, to show that a delayed version of this signal has transform 1 over z to the m x of z. So a delay by m samples corresponds to dividing by z to the m power. Okay. You'll also see this written as multiplication by z to the minus n. So a delay of one sample corresponds to multiplication by z to the minus 1, or dividing by z. And it's important to realize, understand what this sequence looks like. For example, this x of n, u of n sequence could be a sequence that looks like this, goes on forever. It's 0 for negative values of n. This delayed sequence actually is 0 now out until we get to m, and then we would see this sequence at m plus 1 and so on and so forth. So let's look at a couple of examples where we apply this delay property. First example will be fairly straightforward. So let's call it example A, where x of n is n minus 1, u of n minus 1. This would be, we want to find the Z-transform of this signal. So and this is a delayed version of the corresponding undelayed sequence. It would just be n u of n, and I can look up the transform of this wn sequence. The corresponding Z-transform is right in my table. It's z over z minus 1 squared, and then I can see by substituting n minus 1, n for n everywhere it appears in my definition of my wn sequence, then I get this corresponding x of n sequence. So x of n is a delayed version of w of n. It's delayed in this case by one sample, so I divide by z, multiply by z to the minus 1, and the corresponding Z-transform is just 1 over z minus 1 squared. Let's take a look at a slightly more complicated example. Again, often you have to resort to various algebraic tricks to rewrite the given sequence in such a way that it matches a pattern that's given in our table of Z-transforms. Of course, this particular sequence doesn't become non-zero until n equal 1, so it kind of looks like a delayed sequence, but I need to actually force this into the form n minus 1. I need an n minus 1 times u of n minus 1 in order to apply this delay property. So again, there's a little algebraic trick. I'll just add and subtract 1, and this becomes n minus 1 plus 3 u of n minus 1, and now rewrite this as n minus 1 u of n minus 1 plus 3 u of n minus 1. Okay. And so the corresponding Z-transform is, we just found the Z-transform of this component in part A. It's 1 over Z minus 1 squared. And then this is just a delayed unit step. A unit step has a transform of Z over Z minus 1. So the Z-transform of this would just be 1 over Z minus 1. Of course, it's multiplied by 3, so I'd have 3 over Z minus 1. I can combine these by multiplying the second term in the numerator and denominator by Z minus 1, so we'll have them over a common denominator. Then with a little algebra, rewrite the Z-transform as a ratio of polynomials in Z in this form. Okay. I guess one other case you may run into that, I'll call it example C. So we've got x of n is n minus 1 u of n. Okay. Again, this looks kind of like a delayed sequence. It's not. It's first non-zero at n equal to 0. So the trick here is actually just expanding this like this, n u of n minus u of n. Okay. And then so I can get the Z-transform of these components really quickly. I have to just directly from my table. So I want to differentiate between the u of n minus 1 or n minus 2 cases, which are truly delayed sequences that first become non-zero at some value of n greater than 0, and a sequence like this, which is non-zero first at n equal to 0. So it's not really a delayed sequence at all. I'm not actually using any delayed properties to find the Z-transform here. I do have, I want to look at some related examples. X of n minus 1 times u of n. Now this is slightly different than what we had before. Again, I'm treating here x of n as this infinite duration signal or everlasting signal, and I'm interested in the Z-transform of this signal, where I've shifted just this everlasting signal to the right by one sample and multiplied it by u of n to make it now a causal signal. And how is it related to x of z? We can actually show by that this is equal to x of n minus 1 times u of n minus 1. Okay. So these would be identical sequences for all n greater than or equal to 1. The only difference is this has a term at n equal to 0. Well, I can just add that term in. The value of this sequence at n equal to 0 is x of minus 1 delta n. Okay. So these two sequences are identical, and so now I can find the Z-transform of this sequence. It would be, of course, this is just our delayed component. Just applying the delay property here that we just covered. So the Z-transform of this component is 1 over z x of z. And then I would have the Z-transform of this constant times delta n. The Z-transform of delta n is 1. So I'm just left with x of minus 1 here, this constant term. We'll be using this property actually when we apply the Z-transform to difference equations. Just continuing this process, then Z-transform of x of n minus 2 u of n would be, I would just multiply all of this by 1 over z, so I'd have 1 over z squared x of z and then plus x of minus 2. And there's some similarity here between these shifted sequences defined like this and the differentiation operator in Laplace transforms. One key difference is that we were subtracting the initial conditions in the Z-transform. Here we're adding in these initial condition terms. Okay, let's take a look at another property, the advanced property. We won't be using this as often as the delay property, but x of n plus 1, this would represent my everlasting sequence shifted to the left, and then I make it causal by multiplying it by u of n. You can, by directly writing out the Z-transform, using the definition of the Z-transform from its summation and comparing it to the summation of x of n, u of the Z-transform of just x of n, u of n, you can pretty easily show that the Z-transform of this sequence is z x of z minus z x of 0. One final property which will be really important in finding the forced response or the zero state response of our discrete time systems is this convolution, and you can probably guess at this point that the convolution of two sequences transforms into the, no surprise, the product of the corresponding Z-transforms. Okay. So, and we can find the forced response or the zero state response of any system if we have the impulse response of that system by convolving the discrete time input with the impulse response of that system. One approach to do that, instead of explicitly carrying out the convolution, is to find the Z-transforms of the impulse response and the input, multiplying those Z-transforms together, and then finding the inverse Z-transform. Usually in finding that inverse Z-transform, we'll have to do a partial fraction expansion. So, similar to what we did with the Laplace transform approach in continuous time systems, it seems like a lot of work here in the Z-transform domain, but typically it's less work than actually trying to explicitly do the convolution in the sample domain. So refer to table 5.2 for additional properties. These are also on the handout I provided in class. So it's on the back side of that handout. The front side had transforms, transform pairs. The back side lists a bunch of Z-transform properties.